Hello everyone and welcome to a new video which is part of a new series which I'm gonna call What's in a Codebase, most probably. In this series what we're gonna do is we're gonna try to explore large code bases without any filters. So I'll just do sort of live exploration, maybe even judge it, roast it, whatever. And I've picked grpc for this video, so this is gonna be first one. It's gonna be a light one. I figured grpc would be a easier repository to go through. I did a tweet asking about some suggestions and I got quite a few good ones. I'm planning on doing Chromium, SQLite, and I think I also got some good ones like Prometheus and Node.js and Linux, of course. But for today, we're going to start simple. We're going to start with grpc and we're going to pick up the Go implementation because in terms of hindrance that you're going to get due to the language, Go provides the least in my opinion, as it's a very simple language, if not the simplest. So yeah, that's what we're going to pick. And yeah, so I've not really explored the code base. I mean, what I've done is I just went here, did grpc codebase golang, got it, git cloned and opened it in VS Code. And here it is. Hey, it's me from the future after I have recorded the video. Initially, I did not know how the video would look like, but now that I've done, let me give you a brief overview so that you can jump to the parts if you like. So I'll timestamp each of the exploration sections which we explore. We explore some interesting parts like how they are managing memory, how they are compressing, decompressing. We also speculate about things like why they have multiple compressors and multiple decompressors. And then we see, okay, that's the reason. And it turns out I was right. We also see parts where they have implemented their own HTTP 2. And in the end, we will see a whole recap of what we covered. So I'll timestamp everything, but I do recommend watching it from the beginning if you just want to have fun. Maybe, I don't know. Please make sure to leave a like and subscribe and let's go. Pretty famous. It uses HTTP 2 as the wire protocol and it is pretty efficient. If you don't know what grpc is, you can just think of it as a remote call to some function, just like an HTTP call. Honestly, there's not much difference between an HTTP call and I mean a REST API based on HTTP and grpc. In fact, I think you can pretty much replicate everything using REST APIs. It's just like you go to a URL and you ask the server to run a function. They're just used in different contexts. Okay, so that's what it is. It's all about running remote functions using some URL essentially, and it uses HTTP 2 as the wire protocol. Yeah, that's about it. That's the high level understanding you would need. And yeah, so first thing you want to do is you want to read the readme. Other than that, there's usually a file called Contributing.md which you can go through. However, this is mostly things related to code of conduct, how to raise a PR, not much about the code base itself. So we are just gonna go and dive into the code base. So this is the code base, pretty small, honestly. There's a documentation one, which is usually a good idea to read, and you can read through these if you want, but it doesn't look like it is that informative because I don't see what is the entry point. But anyways, we'll read it if we need it. Now, generally in Golang, what you have is you have the interface at the public side of the package, and then in the internal, do they have an internal package? Yeah, they have internal package. In the internal, you have the package specific code, which is not visible to anyone who is importing this package. So what I'm guessing is here we have the general entry points for this code base. So if you imagine a code base as a sphere, the surface area is the interface, the way you interact with the code base and the implementation, and the volume is the implementation. So generally it is easier to understand what the surface area is, what the interface is to use it. You should really not need to know about the implementation. But since we are going to dive into that, we're going to go through it anyways. And yeah, so CMD is usually the, I think, the entry point. Yeah, this is the entry point. It has a main function, and these all other things are sub packages to grpc, right? They have authorization, they have backoff, balancer, benchmark, scripts, all these things. And then they have the more common interface here. Now when I say interface, I don't necessarily mean the interface construct as a programming language construct, right? I can, what I really mean is it's just a way to interact with the code base as intended. Okay, so it can be just a simple struct with a few public functions, and that's quite as well an interface to the library, right? And then in the internal one we would have a lot of stuff. Okay, so this is generally the layout of the code base, but it can be different. It really depends. All right, so let's start. So we have a lot. So first of all, we'll start with the most publicly available files. So these are all in the same package. That's how Go works. So they have a doc. This just has the license. Okay. Back off. So back off is just how do you wanna do exponential back off, I guess. I mean back off retries. So these things are, I want to see what is like the more common entry point to this code base. So client connection might be so this okay, this is creating a new client, which is this, which has a few things. Okay, we'll come to it later. We have codec. Okay, so codec is just the encoding decoding format, and I guess so yeah, they have this base codec interface which requires marshal and unmarshal. Take any struct, marshal it into a buffer slice, which is just an array of buffer, and a buffer is what? It's an array of buffer. Interesting. So offers a means to represent data that spans one or more buffer instances. Okay, I thought buffer would simply be a type alias for byte, but okay, so buffer slice means a list of buffers, and a buffer has all these things: the read-only data, the reference, free, length, all these things. So as you can imagine, these are supposed to be private to this package, and these are supposed to be public for the clients. And I'll be using this client and a user a lot, but it really depends on the context, right? Right now, so if I'm somewhere here and referring to client, then I'm obviously referring to someone using the package. But if I'm inside internal, then the client might as well be this package itself. So anyways, this is what a buffer is, and notice that this is inside this package, memory buffers. So yeah, mostly it's like all these things are the interface to this package, grpc-go, and then the internal will have most of the implementation. These will also have implementation, but not that much, is what I imagine. Okay, let's see if it has any implementations. We have an empty buffer and a slice buffer, and yeah, it's one of the implementation is just a wrapper over an array of bytes, which is pretty obvious. And the implementation is also pretty simple. So yeah, let's start with codec only. So this is the base codec. What are the implementations? Yeah, so proto is one of the implementation, right? Makes sense. They use proto buff for encoding, decoding, serialization, deserialization, and then send it over wire protocol, that is HTTP2. Good thing about HTTP2 is obviously that it has all those things like header compression, and what it's binary. No, actually I don't remember a lot of good things about it at the top of my head, even though I've implemented it once. But yeah, it's mostly, yeah, it multiplexes a lot of HTTP payload, so that's also a good thing. That's why they use it by default. I'm not sure why they have not migrated to HTTP3. Actually interesting. grpc HTTP3, why not use, right? So okay, it's still an IETF draft as per this. Are you sure? Okay, water break, sorry about that. So okay, so they are considering it, it's fine. So I was like, is there any reason they have not supported it yet? Doesn't seem like it, other than it just takes time. So codec v2 implementation with protobuf, it's the default codec for grpc like I said. And we have Marshall implementation, which just extracts message out of it. So it could be a message v1 or v2. What are these? Message v2 used by the current protobuf, and v1. Okay, must be something related to the protobuf library, as you know we are here. So I really like to know when I'm looking at a file where I am, because that gives out a lot of information about the code, its user, its client, its responsibility. So that's why I love having this and also having this. I know some people do not like knowing this, but I actually like knowing where exactly in the code I am. Anyways, so yeah, so we have some checks. Buffer pooling threshold, which is 1024 bytes. Then we do proto.marshall. So yeah, it looks like mostly like a wrapper over protobuf package, which is this, right? Yeah. Okay, so the good thing about, so you might be wondering why a wrapper, right? So besides like obvious technical requirements, a good thing about having a wrapper is you can, I mean, you don't care how the internals of the package you are depending on change. As long as its interface remains the same, you can wrap it into your own required interface. So let's say you required okay, let me just say, let's say you require these things. You require a function f and a function g, and you are assuming that g would always exist there in that package, and maybe it does exist because right now they have it, but eventually they remove it because it was not part of the like the main core API. Then this dependency usually breaks. So sometimes a wrapper is usually convenient, and in a language like Go, honestly, I really like these wrappers because they keep things nice and clean. Obviously it adds indirection, but it's fine because it is wrapping over an entire library. But yeah, it always depends on the context. Here it makes complete sense to do this wrapping, somewhere it might not. For example, anywhere you want to do protobuf marshall, you may not want to use this codec, just directly use the proto marshall. So it depends on the context as well. I was just giving one reason why you would want to do that. So I was looking at this implementation, and okay, so we had marshall. Oh, it also has a name. Nice. So codec looks pretty simple, right? Let's go back to here. So we have this is dialing. Doc did not have anything. Interceptor. Where's the server? Okay, server. So yeah, this is small file with only 2200 lines. That looks simple. So I want to see if they have any interface. They have a server options registrar, and okay, they don't have an interface here, but I think they must have this. Yeah, they have this. So why did I know this? The reason is, at work I do use grpc. Sometimes I have jumped into the internal Golang package, never really explored it properly though. Really all I know is I think I've gone through this package once called server, I mean this struct once only, for an issue I was debugging, because most probably it was due to some grpc internal. Okay, so let's look at a server, right? So it has a few options. Options are implemented using this option interface. So basically these are all the options, and then you have default server options, empty server options, and some other things, right? And what you can do is you implement this interface. Where's this interface? I forgot. Okay, apply. And so if that implements it, you can use it. So for example, if we check this, okay, this does not have it. Are you kidding me? Okay, it should implement it, obviously. Apply. What? Okay, good. I'll just look at the implementation. Oh, okay. So empty is implementing it. It does not apply anything. Okay. Join. Okay, you can join, and then why do they have this specifically different? I thought function server option would cover all of them. Okay, cool. Where were we? That was a detour. So we have server options, we have a guard, we have listeners, and then we have connections that have been established, I believe. Then we have serve, drain, some concurrency controls, service info. Oh, can a server have multiple services? I did not know that. Quit, done. So yeah, pretty simple, right? It has a bunch of bookkeeping variables, a bunch of synchronization variables, and mostly this connection, which is keeping the track of state and listeners. Then let's have a look at the functions it has. So honestly, Goland, the JetBrains IDE is a lot more, a lot better to use for Go, but I don't have the individual license for that, so I'm using VS Code. So I might be a bit slow at navigation. So okay, what I want is a capital letter. So let's see. Do they have a new server? So they do have a new server, and the way it works is, the way you create a server is you apply all the options. So this is a common option pattern in Go. You can have a look at it by going here. It is pretty dysfunctional. I don't know. It is okay. Essentially what you do is you have a bunch of functions. So you have all these things that can be optionized. I don't know if that is even a word. And then you take where is the final implementation? Yeah, then you take all the an array of options, and then you just apply, and that apply function really just sets the whatever value. So if it is with host, it will take a pointer to the thing that you are applying and then just update it. So you must have remembered, right, that option interface, it's the same thing. It just applies these options to the option struct, and then this is stored into the server struct. So here, so it's pretty simple. Let's go back to new server. We have a server. It has just initializes everything empty, makes sense, adds the server interceptors. So interceptors are really just things that act before and after a request, if what I remember correctly. We can look into the interceptor system in just a moment. If there is tracing enabled, they have this. What is this? Enable tracing. When is this set? So in Golang, I can just directly go to the writes, but here I cannot, or I don't know how to. So this benchmark, if enable tracing. Interesting. I only saw equals to false. Who knows? whatever, don't care about that part, right? Then we have, okay, so it creates a bunch of workers which will do the work obviously, and then that init server workers, what does that do? So it has, okay, let's have a look at it. Creates worker go routines and a channel to process incoming connections to reduce the time spent overall. Okay, so these workers are given. So what we do is we create a worker channel and a close, and it's part of the struct, so it is initialized here. And then for the number of workers, we create a worker go routine, server worker go routine. And yeah, they take input from this worker channel and run the function f, which is whatever the channel will provide. So channel, it will itself give a worker. So it's a pretty generic worker pool implementation. And yeah, that looks like it. Nothing more interesting here for now. Let's move on to other things. We'll come back here because it's the most interesting part actually. But yeah, I saw this stream. So do we have an interface? Yeah, we have. So another thing I like about Go, we have only interfaces. We don't have abstract classes. So we know exactly what is part of interface and what is not. I mean, what is supposed to be public, what's not. So yeah, coming back to stream. So a stream should have a context, but it is deprecated. Use these instead. Okay, this itself is deprecated. Yeah, client stream and server stream. So yeah, obviously this package is used in two ways, right? One where you are listening, I mean, one where you are receiving, right? That's the server. And one where you are sending, that's the client. Obviously server also sends, client also receives, but we have client stream and server stream separately. We have header, trailer, close, send, context, send message, receive message. So it's pretty simple code, right? It has a header, it has a trailer, it has close send, which closes the send direction of the stream. It closes the stream when non-null error is met. It's also not safe to call close send concurrently with send message. Okay. So yeah, and documentation is also pretty obvious. We have a context to make sure, context correctness. So just like in C++, you have const correctness. In Golang, you have context correctness, where you make sure that you stop async operation, or not async, rather long operations before. I mean, you just simply honor the context. If it is cancelled, you stop. Then you have send message, which sends message, and receive message, which receives message. Let's have a look at this. Called by generated code. Send message. Yeah, so what do they mean by send message is called by generated code? So the way you use grpc is you create a server in a protobuf file. So let's go to this actually. Yeah, so you create a, do they have quick start? Yeah, so you create a server like this, grpc service. You have a grpc, so it's like a REST API with request and response defined like this. Then you simply generate the protobuf code using proto-C. So what this does is it translates this code into whatever language you're using. So you can be using C++, it will create a C++ tub for your grpc server that automatically interacts with this library. And if you are using Go, it will generate for Go. So that's the good part about grpc, that you define the service, the messages in one language, protobuf, and it generates for any language you would want. So you can imagine if your server is in Go, client is in C++, the client will also generate protobuf files from this file, server would also, and the client and server would be able to interact as long as they have that socket information, which is probably just the IP address and port, right? So yeah, and then you have to implement the actual implementation in your whatever language you're using. So go here. Yeah, that's what grpc looks like. So that's what they mean by is called by generated code. So whatever code they will generate, which is usually in .pb.go, right, this will generate, that would call this function for each of the rpc in whichever way it needs to. So yeah, whenever a function or method or anything has such large documentation, you really need to read it. So let's read it. It's generally called by generated code. On error, aborts. If the error was generated by client, the status is written directly, otherwise EOF. Okay. Receive message for unary or service streaming RPC. So what unary and service streaming mean is, in unary RPC, you give a request, you get a response. In streaming, what happens is you send a request and then you can receive multiple responses. So a stream of responses. So you can imagine if you have a very big file, you would use a stream RPC for that. Okay, flow control to schedule with the transport. Obviously, it will have to block until it cannot send. Stream is done, stream breaks. So yeah, now obviously we are just having a high level look. The more you go into the code base, the more you will have to think about each and every line here. Right now I'm sort of just skimming it, which is fine, but if you have to work with it, you will have to read it like your life depends on it, because you should care about the quality of your code. If you do not, get out of here. So let's have a look at the server stream actually. So this looks pretty similar, right? And in fact, it is pretty similar. But where's the client stream? I wanna do a parity check. Why did they even separate it out? So I'll just keep it here. And then, please don't mind me, I'm very slow at code navigation in my personal laptop because I do a lot of work at work, so and everything is not synced properly. So we have set header, send header, set trailer, context, send message. Yeah, mostly similar. Obviously there is some parity, close send, and you can set header, send header. Obviously probably just depends on the implementation, I think, because they were getting along pretty well with just this interface, right? So yeah, whatever. And there's quite a lot. Let's have a look at one of the implementations of the, let's say, actually I want to look at the server stream, because why not? So let's look. So this is probably the main implementation. There, as you can see, there is a lot, and most of them are inside generated files. So let's ignore that. We have one call metrics, which is just a wrapped one. It takes another and wraps it with something. Probably not that important. Probably just adds metrics to the call, like that suggests. Then we have a, I don't know what that is. Reflection grpc, must be some feature. Labels attached string, pretty obvious. So let's look at the main one. This is the yeah, this test. So yeah, this is the main one, obviously. And this has, once again, you would have, so yeah, in the stream it has the compressor, decompressor. And so what is this? A compressor is an interface. Yeah, use package encoding, obviously. That's what I thought, right? Why do they have this when we had this? So encoding package also defines compressor and decompressor, which has a compressor. So once again, the interfaces are so neat in Golang. You have the writer and the writer. I mean, if you want to compress something, you take a writer to it. Actually, I wonder why not take a reader, right? Shouldn't you take a reader and return a writer closer? Oh, wait. Compress writes the data return to WC. What is WC? To W after compressing it. Okay. So see, decompress is pretty obvious. It takes data from R, decompresses it, and provides the uncompressed data via the returned IO.reader. Yeah, this is pretty obvious. Why the compress? Why couldn't it be IO.reader and then return IO.writer closer, right? I'd write closer. So by the way, if you don't know, reader is a pretty simple interface. It allows you to read for, like, you give it a buffer and it allows you to read into that buffer, or rather read data and then put that into this buffer, and it will also return the bytes read and if error any. Similarly, you can write yes, so similarly you can write whatever the buffer you have provided to whatever the write is supposed to write to, and then it will return the number of bytes returned and any error if any. And then closer is something that just have a close function which is supposed to be called at the end. And so read closer is something that has a reader and a closer. Write closer is something that has a writer and a closer. Then we have read, write, or closer, whatever. So compress, let's actually look at some of the usage to see, right? So we have a compress utility where we have some stuff. So W, okay, actually let's read it properly. Compress returns the input bytes compressed by compressor or CP. So CP is the compressor. If both compressors are nil, okay, so this takes two compressors, CP and compressor. Great naming. If both are nil, or if the message has zero length, returns nil, indicating no compression was done. Okay, it's a to-do by some guy. I mean, could be anyone. So but this to-do, has this to-do been there for a long time? I'm actually interested. 7 years. Classic, right? That's classic. So what you do is you want to compress this buffer slice. You have these two compressors. This is the older one, this is the newer one, and then we have a memory pool for allocating memory, I believe, right? Buffer pool is like you can get a buffer of this size and then put. So the reason people usually use a buffer pool is pretty obvious, to ensure that your memory does not go beyond a certain limit, right? So it's like an arena for memory. If you look at the implementation, right, let's go to, see, we have a leak check one, you have a shared buffer pool. I want to go to the most basic one, simple buffer pool. See, we have a pool, and what this does is it has a capacity. No. What's pool? A pool is a set of temporary objects maybe saved and retrieved. Okay. See, the simple buffer pool, the way it works is you have a pool of something. Okay. It doesn't look like a typed API. So, but the way it works is whenever you want to request for this many bytes, you get from this pool, cast it to bytes. Okay. And if you have greater than this size capacity, you return that. Okay. You update that as well. I don't know how this works, as in like how it is syncing with pool, but it probably does. I've never liked the sync.pool API anyways. So, and okay. Yeah, and if it was too small, it puts it back to the pool. So yeah, this is just like a memory capped memory allocator, right? You allocate this many memories as bytes, but it cannot go beyond a certain limit, so it will ensure that you never go beyond a certain limit. So again, it's a pretty good one, right? Even at our even at my work, like I work at the database engine layer for my team, so we have something like this as well. And it's pretty sophisticated because we have different needs, they have different needs, and it is one of the more important things to make sure that backups and restores don't easily go out of memory, because the amount of data we back up and restore is so much that we really need this proper memory pooling. Okay, so as you can see, we are creating a writer using pool. So see, this is very interesting part of the code. I really like it. They have a small little memory package which they use, and it's just nice. I just really like these small implementations which do most of the interesting work, and like they don't have a whole dependency package for this, because they can customize it to their own unique needs, and they have done it, right? If you go to this, okay, so if you go to the pool and then you look at the implementations, they have some pretty interesting implementations like leakage. So they have a tracking buffer pool. So they take an internal buffer pool, right? And then they wrap it with some tracking. So whenever you increase the number of buffers you have allocated, and then you also figure out, so sorry about that. So you also figure out information about that buffer, right? So you create this stack which you get by using runtime.caller. So what this does is, whenever you call this .get, it will track at which line of code through which stack trace. So who was the caller, up to 16 callers, I believe. Oh no, it's skip. Oh, okay. So also I'll explain why skip is there. So it will go up to, I think, 16 callers or something, and capture that information, so that when you are actually debugging and you see, okay, this line and this this allocation will happen at this line and with this stack trace. So you would also have a pretty good understanding of what workflow must have triggered to go through this stack and then call an allocation. And I really like stack traces because they make debugging 20 times easier. In any sufficiently large code base, you always need stack traces, because a single line of code can be called from many places. Okay, and then skip, really what skip is all about is, when you call runtime.caller, I mean, you can obviously see what skip does, but essentially it will go and I think it will get the callers using, so when you get the stack trace, you will get the stack trace from here, this line, but you don't want from here. You want from, not even here, you want from whoever called this .get, so that you know actually who is the client. Otherwise you'll have to every time eliminate the last two callers from the stack to get the actual caller. So yeah, and then similarly you have put. So put is just deallocation if it was not free. So see, you can also check if it is a free before use or something like that sort of bug, and then you can delete. And I think this would be used in tests, not sure. Okay, they don't have set tracking buffer pool. Yeah, see, they have one in grpc test, transport test, yeah, and like this. So pretty, see, that's why I said Golang code is very easy to read. It reads like a book, and you can also make assumptions about code, and they turn out to be correct mostly. So actually I want to look at more. I mean, allocators in themselves is it's a pretty big topic, right? So we can spend whole day on it, or we can just go back wherever we were. Yeah, we were at compressor. No. I think we were at a compress function. Yeah, we were here. So you create a writer and then you say compressor.compress. So if compressor was provided, it will use this, the older one. Otherwise it will use the newer one, I think. Where is compressor used? No, sorry. Yeah. So if newer one was provided, encoding.compressor, use that. Otherwise use the older one. The way newer one works is you provided a memory area where it's gonna write the compressed data, and it will give you a io.writer, and then you write to that io.writer whatever the data is. So from input, I think, yeah. Yes, again, I still don't get why would you not give it an io.reader. Maybe because you would have to do the same thing here. So the way I was imagining the interface would look like is you would have I'm gonna write it here so that it doesn't ruin the navigation. So it would take an io.read closer, it would return io.write closer, error, okay. And then let's go back, and then here so this is the memory. Okay, actually it makes sense. Does it make sense? Nah, it doesn't make sense. So we would do something like this. So whatever this is, right, so you can okay, I'll just yank it like normal people. What? Okay, I'm bad at Vim, leave me alone. So this would be wrapped, okay, you know what, screw it. So this would be wrapped in a reader. So function read more, let's just say this is a function. So closures are pretty powerful. What am I doing? I've forgotten all languages. I was doing Haskell. So, and Haskell doesn't even have that syntax. What am I doing? So this is a closure you create, and then what you're doing here is yeah, that this makes sense. So basically what's happening here is, right, I was saying we'll have a read closer, and then whatever we are reading here, read only data, we put that into that read closer and then pass it here. From read more, let's say this gives a read closer, okay, and then you'd get a write closer. But this is actually not great because this will require multiple copies of the data. So I had a hunch that the API is to avoid multiple copies of data. I guess it's the reason. So the reason they have this is because here you just give it the allocated memory. It will give you a writer where you write, and then it will write here. So you don't have to create any staging area for you. But if it asks for a read closer, you have to create a staging area there, but that probably already happens inside the compressor. However, the main problem is the write closer you have given doesn't directly write to the memory region, right? So probably something like w.io.writer, so that it directly writes to the memory region you want and not like providing an arbitrary one. So that would have been something like this. But okay, fine, I accept this API. Excuse me. Similarly here you have yeah, see, man, I was right. See, this is obviously really inefficient since it fully materializes the data, but there's no way around it with the old compressor API, because this old compressor API only has this. It has exactly what I said, right? The original API that I thought, which is the more intuitive one, obviously, is you give it the input and give it the place where it has to put the output, but this requires an extra copy of the data. However, and if they take an io.reader, maybe it would require less copy of data, but still copy of data. So that's why they have this a bit more roundabout interface, but that is more efficient. And I am already lost. So yeah, this go back, which is command and left bracket and command right bracket for go wherever I was. So undo, redo sort of in terms of navigation is very useful. So yeah, and that is why they have this whole thing. That's why they added this compressor. And I think if we look at this, right click to see commit actions. Can I see the commit? Yeah, so if we go here, okay, this is probably fixes 803. Okay, probably unrelated to whatever we were looking at, but yeah, this was a nice little optimization that we saw ourselves, right? But yeah, that's why you shouldn't like immediately go and criticize an API just because it looks funny, because it probably has a reason. People who code important projects are generally not that stupid. Generally, okay. Okay, what have I changed? DS store, great. I work in Mac. Did you know that? Probably not. So yeah, now we know why we have this old and new compressors. And we have a method logger and all that crap. What I want to see is send message, because these things pretty obvious, like however they are storing the header and stuff, just add that header. Not that impressive. S is just the transport service stream. Huh, whoa, what? Does it implement something? If it has all these things. Okay. Server stream. Oh, no. Server stream interface. Who implements this? I thought that capital server stream is also implementing it. Well, whatever. Who cares? Who cares? I don't. So send message. Okay. This is just a cleanup, I believe. Lazy log. If there was an error. What is tr info? Trace info. Okay. And if there was an error, then we convert that error to RPC, and see, it's pretty simple code. If it was context deadline, convert it into a grpc error, which is just a status error. So yeah, this is also an interesting package, I believe. I mean, not that interesting, but so what it is yeah, it is inside. Yeah, so this is also another thing I've seen sometimes. What Golang projects do is, so something is some interface, right? Again, interface doesn't necessarily mean interface. So is added in a internal package, and now they want to expose it to the client. So what they do is they create a type def like this using equals. So you can do two things. You can do this, or you can do equals. Equals means the types behave completely equally, and this would mean that you have to they're internally the same type, but the methods that were on here are not here. So you can define newer abstractions with the same inner data. So they do this on a publicly available package so that clients can see it. And this just has a code message in details. Yeah, it represents a grpc status code, and we can create it using any of these codes. So we have unknown, invalid argument, deadline, and if you see this maps with like this is 400, right, from REST API. I don't know deadline exceeded but not found 404 already exists. I think 409 or something. I think 409 is for conflict. Permission denied 423 or 413, I don't know, something like that. So it's the same thing, it's just more concrete, I think. And depending on the error, it does some translation and then returns it. Okay, interesting. I mean, not that interesting. Let's look at the actual code. Again, water break. It's really hard to say this much while looking at code. All right, next. So what it does here, right? How do you send a message? Message can be anything. It's just an interface. How do you do this? So yeah, of course, I'm skipping over a few things about the Go language, but I do hope that you Google those things along the way to understand things better. For example, what is an empty interface? Empty interface is something that requires no method, so every type implements it. So it can be used for any type. It's like any from TypeScript. So what you do is you compress. Yeah, I wanted to see what the heck is this transport. Okay, it's inside transport internal. Okay, cool. Yeah, so I believe. Honestly, better navigation tools would really help, but I have just never invested that much time in VS Code. So yeah, here we are creating a new method. You know what? I don't care. So it's something. Okay, it's something. I'm pretty sure it does implement that. Where was that? ss.s. Bro, come on. Yeah, I do think this implements that that interface service stream, read, send it a write status. No, I think it's not. Receive, compress. Okay, maybe it's not. Yeah, it's not. I don't know. In Golang, I can easily see which type it implements. Can we see how to see which interfaces a type implements Golang VS Code? No, I already know. No, I already know this. Yes. So inverse implementation, okay. Okay, actually let's look for this because we know this implements one of them. References, if I go here, not here, so references does not show you. Go to implementations. Oh, okay, you have to go to implementations. Cool. Let's go to implementations. Yeah, so it implements this different one, and it's an experimental one. Okay, so it's not that. It's just some internal type which is a helper for the actual server stream. Okay, that's okay. We can have a look at that later. Streaming functionality for a gRPC server. Yeah, so we use that to compress. Returns the send compressor name. Okay, it just returns the compressor name. Okay, so we prepare the message. To prepare, we use the encoder, right? So first of all, we encode it using the codec and the data we want to encode. Then we compress it. This is the function we looked at. And encode, I think it's pretty simple. We just pick the codec.marshal. If the length is greater than this message too large, we set the header. We are setting the header. No, this returns the header. Obviously, it usually when you just have the name as a function, it gets it, and when you have set before it, it sets it. So prepare method, message, then whatever data you have allocated, you make sure to free it, and that's why it is in defer, because there are multiple workflows, right? It could return here, it could return here, it could return. Okay, there are 3 places to return, but anywhere we return, we make sure to free the data. Okay. Interesting. Yeah, so that buffer also has a free. So see, and now because they made their own little memory package with the buffer, with the pool, right? What was that called? Memory pool or something? So they have it coupled with this buffer interface, and that makes them work really well together. So it's often a good idea to implement things yourself if they're not like extremely complicated, because then you have a lot of control over it, and based on your specific use case, you can even optimize it more than any generic library can be optimized. So okay, so send max size is also here, which I think we can set in the new, yeah, based on the options, right? And I think this is 4 MB by default. Can we check? Let's check that. So options, send message. Send message, where's that? Yeah, so yeah, let's look at the default one. Where's that? Okay, max is u in 32, in 32, which is to the power 31, I think, but the maximum receive is 4 kilobytes. Wait, what? How much is this? So 1 byte, 4 bytes, 4 kilobytes, 4 megabytes. Obviously, 4 kilobytes is nothing. It has to be megabytes. Okay. And then we write again using the internal one. So yeah, and then based on this, we have bin log. What is binary log? Okay. For each method, we have a different logger. Interesting. And then stats handler. Okay, what is this? Huh? What is this? I've never seen this. Oh, essentially you can tag a connection by adding, let's say, more key value pairs to the context. Context is something that again, I would just recommend look it up. Okay, what is that? but essentially you can call it's a key value pair with some synchronization primitives, like when you want to cancel a grpc, it will have a channel that returns some value. These two things. So you can add few more things based on tag connection. So you can tag, and then it has handle rpc, whatever the output payload is. Oh no, not here, output payload. Yeah, so it creates a struct out of that, gives to handle rpc. Let's have a look at an implementation. So it looks like it is mostly used for metrics and stubbing for test, right? Yeah, so not that important, honestly. Next is, yeah, let's actually look at the server stream that is inside of this server stream. So let's see. This is at the transport layer. So if you look at the internal one, if you look at the internal, God, there's so much. Of course there's so much. Why did I think I can do this in one video? So stream, so this stream is like at the transport layer, what I believe. No, probably not. This does not fit in the OSI model. I don't think so, because we are already at the application layer. So if you see, most of the not most, like many of the external packages will have an internal package related to internal. So for admin, back off, balancer group, all these things, you have an internal one which has a lot more the implementation. And so inside transport you have two. Okay, you have only one, grpc http2, and yeah, so okay, so this looks like an interesting package. Let's have a look at this only. So what transport does is, let's have a look at any interface we have here. So you have the, okay, this is not a very useful interface. Okay, stream. So this transport interface is built on top of stream interfaces. No, not stream interface, but stream structs. Okay, server transport, what does that look like? You can handle a stream. Peer, what is a peer? Mission, okay, whoever is like you are communicating with. If you are server, peer is the client. If you're client, peer is the server. Their address, local address, and the authentication info, sorry. Okay. Server transport. How do we use these transports to build something? Yeah, we use these to build the server stream, right? No, why would we use this? Build server stream? Transport, let's look at the implementations, right? Yeah, we use this to build the http2 server. And then what is it? Implement transport. Then it is used here in the new http2 new server transport, and then it is used in the server in the new http2 transport handle raw connection. Okay, actually let's go from here. So this is the outermost server which we were talking about in the beginning. So it has a serve function which is called, I believe, in the worker. I wish I could filter out the test files easily. Okay, no, this is supposed to be the client facing function. Yeah, this is supposed to be the client facing function. and never s.printf. Okay, if service called after. Okay, so this is just simple bookkeeping. We create a listening socket. Yeah, so the way it looks like it is structured is, which is pretty obvious in hindsight, is we have this server. Okay, and let's go back to the server. So it had all these options, connections, and it has, for each, it has a server transport. So this is the server we were looking at. Okay, and it also has the service info for each service and a listener. Then when you create a new server, wait, no, okay, so let's see, whenever it is used, right, you just afterwards call serve. So dot serve is then called, right? So I think we went on a detour when we were looking at it. We only looked at the new server function. We should have looked at serve as well, because that's how it is used. And that would have been a slightly better top-down approach, but really we are just exploring the code base, so it is fine. So here, yeah, so whenever you say, okay, so you can create one server instance and you can give it a listener, which, okay, which has a way to accept connection. So whenever it accepts a connection, so it's probably like a blocking call, and it returns a connection where you can read, right? So this is like the more TCP layer, sort of transport layer at the actual OSI model, or whatever model we use, layer. So we get that, and then it adds it to its listeners. Then yeah, let's see, okay, I wanna, one moment. Okay, so serve, okay, down. Man, I'm really not used to these keys. Okay, good job. Interesting. Okay, so serve blocks as long as listener listens. So cool, that makes sense. So this means, yeah, this is called using lock, and where it is unlocked is, yeah, here. The reason is, so we have done all the bookkeeping here, and now clients in another Go routine can do another serve so that they can listening at multiple listeners. It's usually not how it is used. Usually you just have one listener, and then as long as we get any raw connection using the listener, what we do is, okay, where's the raw connection? Come on. Yeah, we handle raw connection. The way handle raw connection work is, so some bookkeeping. What the heck is this? Oh, okay. So if the raw connection has passed server transport, then we call that. Okay, I don't know what this is. I really don't know. I don't like this. The way they have this inline interface. But looks like so a connection wrapper can have it. And this is used, a thin wrapper around net. Okay, it's a wrapper around net dot connection, so I think they will always have that. XDS, what is XDS? Okay, looks like something that is used for configurations. So I really sort of, I mean, see, this looks like a hacky code, right? If you go here and you see this, what was this? Handle raw connection. So they should have created a more a non-inline interface, in my opinion. What's the git blame? Come on, how do I see git blame? Git blame. I don't know how to do git blame. Great. Yeah, so looks like I mean, it's fine. Obviously, we should not judge. But I don't like this part. Then, yeah, we have a server streams. So once again, by the way, what did pass server transport did? Okay, and then it adds the connection. So it fills this one, and the connection, wait, okay, it has a map of server transport. So it adds this server transport by so using that raw connection, right? See, what did we have? We had a raw connection which looks like this, which is like a source net. So it's a very raw connection as the name suggests. And then we wrap it using our HTTP2 transport for HTTP2 handling all these things, right? The MAC streams connection. Yeah, so wait, so does grpc has its own HTTP implementation? Yeah, see, it uses its own. It can also use this. Yeah, for some reason it's using its own implementation. Why? I don't know. Yeah, let's see. What was he saying? Okay. Yeah, so actually this looks like just a matter of maturity. The code base doesn't look mature enough to first of all support any transport, or maybe that's not their priority, but interestingly they have their own implementation. So probably HTTP2 did not have all those things, so they just created their own. Very interesting. So that's why, like, I was a bit surprised why even have all those things, right? Because a lot of HTTP2 things should have, like, the core HTTP2 should have been imported, not implemented. So yeah, interesting. And then so once you get the server transport, you handle that, and then you remove after it's handled. So the way you handle it is, first of all, you tag the connection, and then you call the handle connection using sh, which is the stats handler. Okay, good. How does this work? No, this is stats handler. Why am I looking at stats handler? Yeah, so handle the stream. We acquire the stream quota. And then what is F? Okay, handle stream. Enable tracing. And yeah, you can imagine like moving this entire HTTP2 implementation away and then using whatever HTTP2 is provided will be a lot of effort and also might not be as efficient, because right now they have access to all the internals, whichever they want to expose. Right here is the implementation, and it's like it's not a very large implementation. So if they choose not to do this, then they'll have to do a lot of workarounds as well. So yeah, interesting. And that's why it has been here for a long time, since 2016. This has been 2015, 2018, 2906. Yeah, it's been a long time. Yeah, this is exactly what he has said. They would have to do a lot of work around. It's not easy, and probably it's not just that feasible. And he has also provided a workaround. Interesting. What you can do is you can add a wrapper on top of grpc generated code to switch on in process and normal. Okay, it's not a very good one. Yeah, this is just a matter of maturity. I think if you looked at C++ or something like Java, it would have it. So yeah, good stuff. See, this is the reality of code. It is so far from perfect. You may be using grpc in Go and must be thinking it's mostly stable, nothing really happens, but the internal it's kind of screwed. It's not that great, and it's completely fine when you accept, right, that software is not perfect and you learn to deal with that imperfection. That is when you really grow, in my opinion. But anyways, so what we're doing is tracing. I think we are covering most of the parts. We'll do a complete walkthrough once again once we have finished whatever we want to see. We get the method. See, this is like basic string manipulation. Many times you would encounter people in code like, hey, make a variable constant for this, and mostly it doesn't matter, right? It's gonna be slash forever. Why bother? And much easier to read. No, not a very strong opinion, honestly. So you get the stream method. What is this? Okay, you get the position, and then you handle that RPC. So you have the method, you have the everything, header, compression, wire length, remote address, local address, and then you handle it. Okay, interesting. Actually, let's continue. So I took a small break, and I just looked at it, and I think I missed this, but they do have this serve HTTP, but whatever, like we concluded, right, that they have a separate implementation, and it would they have done a lot of performance tuning work on their current implementation. They would need to do a lot of workarounds for the HTTP to the generic implementation, and that's why they don't have it. Was still the correct conclusion. Just wanted to correct this. Anyways, so we were looking at the the handle stream, where we have figured out the method, and then what we do is we just so we have the method we call handle stream, handle RPC using the server. This is handler, stats handler, never mind this. What we do is yeah, we do this. So it has this thing, right? It has this methods and streams. So it's just the RPC methods defined in the RPC service protofile. So if it's a unary RPC, it calls this, otherwise it calls this. And then probably just writing the status and all that crap. So let's have a look at the unary RPC. Some bookkeeping, some stats, tracing info, handle RPC. Okay, no, this again stats handler. Oh, come on, man, this has been clickbaiting me so many times. Where is the actual one? Okay, so we receive compressed data, we decompress it, MD is okay. Yeah, so we call the handler whatever is like attached to this method description that we had, right? So this looks like this, and these are provided by the the code gen that proto-C does. grpc, no, not this one, yeah, proto-C. So this calls the handler. It takes the service implementation, which can be anything, and okay, and then calls that. And if there was an app, what is this app error? Okay, it's just the error. If there was an error, figures out the context. So yeah, it's pretty standard. Nothing of note that I can easily see, but obviously there's a lot of stuff going on here. A lot of it is bookkeeping, as you can see, right? And making it a lot more slim would obviously increase the speed, but these things are really worth it, in my opinion. Maybe not everything, but many things are. And now one thing I'm interested in is where am I? Yeah, the context handling. Does it do anything special with that? See, that's why I hate VS Code. Okay, here. So it takes out the context, and then, okay, what is this context with server? Okay, this just adds a server value, and then trace context. It sets the context, which is stream.context. Okay, why? Okay, so it had taken out the streams context, added some more context to it, right? And used it for the stats handling, and then it sets it back to context. Process unary. Then handle RPC from incoming. Yeah, it doesn't look like anything special, mostly just honoring the context deadline, as you would expect. Handle stream. You can also look at the handle process streaming RPC, which creates a context with server transport stream. Okay, this is the context. It creates a server stream and then uses that. We received that, decompress. So honestly, a lot of just implementation detail here, and not much. Could I write this better? Obviously I can, but most people cannot, so I don't really judge them for it. And yeah, so it's pretty simple. you get the stream, you do all those stats handling, receive, decompress, apply the required function, get the error, handle that, and that's about it. Okay, so let's go back. Okay, I think I'm out of backs. So here in the server, we looked at the handle raw connection, and that's pretty much it, right? Handle raw connection was called here in the serve, and they mentioned they also have a serve HTTP. So this takes a response, okay, HTTP, and this is experimental. It is a server handler transport. Yeah, so we looked at this server transport implement interface, right, in the internal. So this had two implementation. One was HTTP to server, and one was this, which takes a request response, which you get from the generic goes HTTP layer, right, and then adds and removes connection based on that and does things. So yeah, the transport is the main thing in the serve, right? This takes a listener. So if you see any usage, this is taking a TCP listener, right? So that's why the implementation, where's that implementation? I'll just go to server HTTP. I was easily able to find, yeah. So this implementation is essentially the HTTP 2 implementation. We already knew that. We just wanted to go through it once again, right? And they have all those things. They have the framer, which I believe does the frame handling for the packet, the MAC streams, and yeah, I'm pretty sure this is not HTTP 2 completely compliant, but it doesn't matter for them because they are like using their whole own thing over TCP, so they don't have to implement HTTP 2 exactly as per the protocol, but they probably do for the most part. I want to see one thing. Just give me a moment. So Google internally had this stubby. When I was in Google, I used stubby, and it also okay, I'm not gonna say much about it, but yeah, stubby was an RPC framework inside Google, and the gRPC is essentially the open sourcing of that, and yeah, a few things actually got cleared to me today that I really found like a mismatch between them, but okay, I can talk about it, I guess. But yeah, so interesting, they have implemented a lot of HTTP to server here, and what do we have here? So the way this handles a stream is, oh, they throttle. Okay, this for flow control. So they read a frame using the framer, like I said. So frame is just what is inside a packet. I believe frame network. What is a frame in network layers? Oh, frame was that. Okay. Let's actually just have a look at what frame is. Okay, frame here represents the HTTP packet. So it's like this. It's like this, I believe. Okay, so the outer layer is also called frame, but then it has some header. Then there's the IP layer, right? The transport layer has a IP address and a port, let's just say. So this is the header for TCP, and this is called the packet, I believe. And then inside this we have the HTTP2 headers, which we are implementing here, and then the data. So that's why it has all these things, RST and all that. So I've looked at the HTTP2 RFC. So for network things, most of the time I believe just go like this. Look up the IETF RFC, and it is the source of truth. You can just read it. I also implemented it once. So if I go here, yeah, so I did a bare bones implementation which sort of works with a h2 load CLI command. So I mean, it works for some basic handshaking and get request, I think. Maybe I think even post request as well. But yeah, so that's why I have a pretty good understanding. Like when I saw these RST settings, push promise, I immediately knew that we are talking about the HTTP2 frame and not the, let's say, Ethernet frame. And it makes sense. Why would we have Ethernet frame information here? Flags. So this is the frame. Read frame should also be pretty trivial. It's just parsing. And then once we read the frame, based on the frame type, if we have a data frame, we handle the data. So whenever we receive data, right? So for HTTP2, any information is data other than the metadata it uses for its own transportation, right? So that means a header, like let's say content length. Okay, maybe not that, but let's say something like, yeah, anything that goes inside the body is a data. I don't know what I was on. What is this? Send BDPP ping. What is BDPP protocol? Oh no, not this. BDP ping. Okay. I think this refers to flow control. Okay, bandwidth delay product. Interesting. So this is something related to congestion control, but I think congestion control was removed from HTTP2 because it did not work. Well, whatever, it doesn't matter. They might not be setting it actually. So let's see, where is it set? If it is a dynamic window, only then we are setting it. Okay. And okay, dynamic window true. Okay, so in some configuration we use this when the window size is not is pretty small, I think. But anyways, we do this, avoid excessive ping detection. Interesting. What is this? So I don't want this to turn into a HTTP2 code workflow, what's in a code base video. So that's why I am sort of avoiding this. But this looks like something interesting. control buffer. What is loopy? No. I see. So this is a round robin on top of streams or something. Okay. Oh, obviously. So it's like you can have multiple streams active for an HTTP too. So unlike a normal HTTP where you can have only one connection at a time, you can have multiple here. So you have to process them somehow, right? So loopy is the scheduler for that. Okay, interesting. And this must be the way we control it. It's a way to pass information to loopy. Interesting. So yeah, there's a lot of stuff to read here. I mean, this entire package in itself is a monstrosity. Is my caps lock on? No. Select the right stream to dispatch. So this we got by I think we'll use loopy to figure that out. Oh, okay, we already have the stream ID. Oh, the frame already gives the stream ID. Yeah, so in HTTP frame we have the stream ID because for just one socket, the IP comma port, we can have multiple streams. I can prove this to you by just going to the frame. Where's the frame? Where is the frame? Yeah. Come on. Yeah, stream ID. Okay. So handle data, figure out the correct stream, and then we just put into that. This is the state machine. On data, depends on the flags. We do some stuff, and if stream ends, then we also do. Oh, interesting. They're using compare and swap state to do some atomic operations so that they avoid mutex. Nice. So this probably was added as an optimization, I believe. Git blame. Okay, I'll have to see the entire history. Git history. Okay, let's look at the line history. Oh. No, I want to see compare and swap state. What? Okay. Line history. Line history, come on. Okay, here it was added. Okay, it was refactored. No, it was not refactored. But the name is weird. Why is it called revert? Okay, I forgot what I was searching for. Good one. Compare and swap. It was there. Why can't I find it? Okay, whatever, it's fine. So yeah, this just marks the stream done. Get blame, can you leave? Thank you. Cool. So we can also look at something else. For example, handle RST actually. So whenever it says RST, it gets the stream and then it just cleans it up. We have deleted the stream. Now any new packet coming for that stream will require a new handshake or whatever is the first stream supposed to be. I mean packet supposed to be. I think it is HTTP2 RFC. If you look at the state machine, yeah, you have to say reserved. Yeah, it has to send a, yes, what was called, I think it was called prelude. No, it was called something. Issue something like that. Yeah, so it sends some special data and that initializes the stream. I can't find it right now. And if you look at the other one, right, the HTTP handler server, which takes a request and response writer. So the way this works is let's see, peer do write status, write header. Where's the, you know what, screw it, I'll go like this. Handle streams. Okay, so here it must be very simple. You just go over here, oh, we are creating a server stream out of that. Okay, it doesn't matter. I think no. Okay, I don't care enough to read this part, but it's just the same thing. How do you handle stream over this? It's implementing this interface. So oops, this one, right? So given a handler, how to handle that stream. So it converts the whatever underlying stream is to this server stream, which takes in a stream. So okay, so it must be doing some translation. So it looks like it was created more for the general HTTP2 thing, streaming and all that crap, but then to support this HTTP, we have to do that translation. So it's probably not as fast, and we can probably test that hypothesis by going to the git blame. No. 5 years, and if I go HTTP2 server, then I look at this. 10 years. Oh, this is an initial commit. Okay, it's been there forever. 9 years actually. I'm not sure. It's can't say with certainty until you like spend some time on that. But okay, I think that covers it. And there's obviously a crap load of stuff here. We also have something called interop. So there's just so much to explore. Okay, I think we have explored a decent chunk of the code base. We cannot, there's a lot of things that I want to look at. For example, keep alive. Okay, there's not much, but there's a lot of stuff. But I think we've covered quite a few interesting bits and pieces of this. One of the best ways is obviously when you have some work to do into this, then you can actually do some better exploration. This was a bit more hand wavy, but if let's say I wanted to do something, then it would be a lot more concrete, but it would cover a lot less part of the code. So yeah, so let's do a recap. We went through some of the basic, some of these interfaces that the grpc exposes. Then we also looked at, oh, we did not look at connection, but this is what is provided at the grpc to handle a connection, I think, right? I think that's what it was doing. We looked at some interesting things in the codec. Then we looked at the server. We also looked at the stream. Then we went into some internals. We also spent some time looking at the memory one, which was interesting. Inside internal, we looked at the grpc one, http2 and all this. And actually, I don't even remember what else we looked at. But yeah, there's a lot of stuff to look at. This was just one part, I guess, but I don't see anything like extremely interesting that I want to explore here. So I guess that would be it for grpc, right? But as you can see, this is how you explore code base. Actually, no. So right now what I was doing, I was just looking at the code base, seeing what's fun, what's not. You can either do that, or what you can do is you have a goal and you try to explore based on that. But either way, the more you explore, the better understanding of the entire code base you will have, and the better you will solve that specific problem. Sometimes you don't need to, but it's always a better thing to have in your arsenal. So yeah, that is it, I guess. See you.